If anyone can confirm you can hear me, you can see the slides, then I will start.
I can see them very well.
Okay, so then I'll start. Yeah, so I'm going to be talking about the Lasserre hierarchy, or actually two Lasserre hierarchies on the Boolean cube. So here for binary polynomial optimization. And this is joint work with my supervisor, Monique. And in the bottom right corner, you see that I am actually coming from a rivaling European consortium. So I'm not from POEMA, but I'm from Minoa. But Monique said we can just call this synergy, and then the European Union will be happy. Okay, so what is the setting? So we're doing polynomial optimization on the binary cube. So we want to find the minimum, let's say, of a polynomial over the Boolean hypercube. And I'll refer to this sometimes as just binary polynomial optimization. So as an example, you can use this to model maxcut. So maxcut is an instance of this, a special case where the degree is 2. But in fact, this problem statement is very general. So you can basically model any sort of, for instance, binary linear programming in this way. So it's very general, meaning it also has to be NP hard. And so people are interested in finding approximations to this thing. And there's many different techniques available. Maybe people have heard of Shirali-Adams, things like this. But today we're going to be talking about two semi-definite hierarchies, which are both due to Lasserre and I guess also Lilo. And one of them I think everyone knows. It's the one we also saw this morning. It's just the sum of squares hierarchy. But then there's actually another hierarchy which is based on finding density functions, a measure-based hierarchy, which is maybe a little bit less well known. Okay. So for the first hierarchy, which I will call for this talk the outer hierarchy, and I'll make clear why later on, but this is what people know usually as the sum of squares hierarchy. So we have this basic observation that you can rewrite this minimization problem kind of in a trivial way as finding the biggest thing you can subtract from F so that the result is still non-negative on the cube, right? This is definitely giving you the minimum. And now the idea is that you can relax this non-negativity constraint to a sum of square constraint. Or actually, yeah. Okay, and so clearly, if f minus lambda can be written as a sum of squares on the cube, by which I mean that it agrees on the cube with a sum of squares polynomial, it has to be non-negative, and so we get a lower bound on the minimum. Okay, so. For each r, we now have a lower bound on the minimum of f, and the point, of course, is that this lower bound can be computed efficiently if you fix r using semi-definite programming. And this we saw in more detail in the first talk today. So I'm not going to go into that. And now the basic question we're going to be focusing on today is like, what can you say about the quality of this bound, right? So can you say something about the gap between the minimizer and the degree r approximation? And so what is known is that at least you have a finite convergence. So the Lasserre hierarchy actually will always reach the minimum in finitely many steps, namely in roughly n over 2 many steps. And this was shown first in the case for quadratic forms by Fasi, Sanderson, and Perillo, and then later extended to arbitrary degree by Sakai and his colleagues. But nothing is known so far for the cases where the bound is not exact, right? So if your r is smaller than half an n, then maybe you can still say something about the quality, even if you know that it's not going to be exact. And this is what we're going to be doing today. So to be more precise, we show the following. What we're going to do is maybe I'll just put this here. the idea is that we sort of consider the regime where the order R is a constant fraction of the dimension n. And then what we can show is that as long as this is the case, the error behaves in terms of this function. And here, the way you should look at this is you have this thing here on the left, is 1/2 minus square root t, 1 minus t. This is sort of giving the basic behavior. It's something that starts at a half at t equals 0, and then goes to 0 when t equals a half. And then you have some error term on the right. And so I drew here a picture which might be helpful. So again, looking at the black line, this is sort of indicating the behavior in the limit. So when n goes to infinity. And I guess the note is that as t approaches a half in the limit, so it means that r is roughly equal to half an n, we show that the bound has sort of 0 error. And this is corresponding exactly with what we saw in the previous slide, namely that the bound is known to be exact roughly when r equals half an n. But the point now is that we're also able to give an analysis when the bound is not exact, so when r is smaller. Okay, and just to note already here that we do have this this little condition, which is saying basically that our result only applies if phi is small enough. So it kind of means that if you look at the picture, sort of, if you're too far to the left, if t is too small, then we don't get a result. But if you move to the right, and when this phi function becomes smaller, at some point our theorem will hold, and this will just be the result of some technical detail of the proof. Okay, but this is the basic, the main result that I want to talk about today. Okay, so at the start I promised 2 Lasserre hierarchies, so we still need the second one. So we'll introduce that now. And this one I'll call the inner Lasserre hierarchy. It's also known as the measure-based Lasserre hierarchy. And it's again based on a sort of trivial rewriting of the original minimization problem. And in this case, what we're doing is we're saying minimizing f is sort of the same as finding a expectation on the binary cube, which minimizes the expectation of f. And so clearly, if you compute the expectation of f over the binary hypercube, it's never going to be less than the minimizer. But you even have equality, because what you can do is you can just take the probability that assigns probability 1 to the actual minimum of f, and you get the minimum. And now again, you're going to relax this reformulation by considering not all measures, but instead only measures which have a density function which is given by a sum of squares polynomial. Okay, so we consider the uniform measure on B, and now we only consider measures which are given by a density function S, which is itself a sum of squares polynomial of degree at most 2r. Right, so this is what I mean by this sigma of r. This is just sum of squares polynomials of degree at most 2r. And so now what we get is an upper bound for the minimizers, right? So before we had a lower bound, now we have an upper bound. And again, basically for the same reason, you can compute this thing efficiently for fixed r. It's again an SDP. Okay. And in fact, we show basically the same thing for this hierarchy as we showed for the previous one. So again, we're going to be able to analyze this thing in the regime where r is a constant fraction of n, and we get more or less the same bound. The only difference is a factor 1/2. And importantly, here we do not have this condition. So here we really get a bound for every r and every n. And this is because the technical detail introducing this condition is not going to be present in the proof for the inner hierarchy. Okay, so let me sort of briefly summarize the situation. We have these two hierarchies. The outer hierarchy, which is more well known, is just the sum of squares hierarchy on the binary cube. And we have the inner hierarchy, or measure-based hierarchy. And we have the following. So we have a lower bound, which is given by the outer hierarchy. an upper bound given by the inner hierarchy. They are sort of wedged like this. And this is not the official reason, but maybe just to, to remember it, you can sort of see that this F, this outer hierarchy, it's also outside of Fmin and Fmax, whereas this inner hierarchy is sort of on the inside. So it might be one way to remember these names. And what we want to do is we want to say something about the sort of the relative error of these bounds as R increases. And for the rest of the talk, I'll focus on the proof of the first theorem I gave, so on the result about the outer hierarchy. But what we'll actually see is that the result of the inner hierarchy is actually kind of almost like a lemma in this proof. So we're going to focus on the outer hierarchy, but the inner hierarchy will play a crucial role in this proof. And at the end, we'll sort of have both. Okay. So let me briefly outline the key steps of the proof. So the first thing is we're going to be using the polynomial kernel technique to produce sum of squares representations. And this is actually a technique which was first used for this purpose by Hamza Fazi and Koen Fang. And they do this in a paper also from this year, where they essentially show very similar results to what we're showing today, but on the hypersphere. Okay, and actually their proof forms the skeleton for our proof. So definitely also check out this this paper. I'll give a reference at the end. So then we're going to use a symmetry reduction, classical Fourier analysis on the binary cube, and this is going to allow us to reduce our multivariate problem to a univariate problem. Then once we have this univariate problem, we're going to show that actually it's linked to the inner hierarchy, but now a univariate inner hierarchy. And then it turns out that this univariate inner hierarchy can actually be understood. And this is using a link which was used already before also between this inner hierarchy and the extremal roots of the corresponding orthogonal polynomials. And in this case, this will be the Krautchuks. And if you know them, that's good. If you don't, I will introduce them again later on. Okay? So the rest of the talk is just going through these 4 steps, giving the proof of the first theorem. An observation that we'll make immediately, just to sort of make our life a bit easier later on, is that at least for the proof, we may always assume that the minimum of f is just 0 and also attained at 0, and that the infinity norm of f, and I should say maybe this infinity norm, it always just means the infinity norm over the binary cube, right? So whenever I write anything, it always applies to the binary cube. And the reason we can do this is just an argument of rescaling, right? Like our bound in any case depends on the infinity norm, so we might as well assume that it is 1, and this will make it a bit easier to write things down. Okay, so the polynomial kernel technique. So the goal of the whole thing is to find a sum of squares representation of f plus a little bit, and we want this little bit to be as small as possible, right? So remember, we assume now that f is just non-negative on the hypercube, and so we want to make f a little bit positive so that we can write it as a sum of squares of low degree. And so the key idea is going to be to consider a polynomial kernel, which is here kxy, of a very specific form. So what we're doing is we're taking a univariate polynomial q of degree r, and then we're just considering a kernel, which is just a function on 2 variables in the hypercube, which is just q squared of the Hamming distance between x and y. And so the Hamming distance is just the amount of entries in x and y that differ. And so you might say, okay, why is this a polynomial kernel? Because the Hamming distance doesn't really look like a polynomial. But on the binary cube it is, right? By which I mean that there exists a polynomial in x and y which agrees with the Hamming distance on the binary cube. And so on the binary cube, it's a polynomial kernel. Okay, so this kernel then gives you a linear operator on the polynomials, which is just this integral transform, right? So I write it here as an integral because this is the way people usually write this. But of course, on the hypercube, this is just a summation, right? You're just summing like this. Okay, so what is the point? So the point is that if you apply this kernel to a function or to a polynomial which is non-negative, then the result is actually going to be a sum of squares. And this is very important. And the way you see it is, well, we know that kxy is a square, right? It's q square. And so all that we're doing is we're taking a sum here, a weighted sum of different kxy's. So it's a sum of squares, right? That's exactly what it means to be a sum of squares. And the way that you can use this now is by doing the following trick. If we can take lambda big enough such that this expression in red here is a non-negative polynomial, and believe me for a second that k is invertible, so this makes sense. Then we can do the following trick. So we write f plus lambda just as k inverse of f plus lambda. But now this k inverse of f plus lambda, by assumption, is a non-negative polynomial on the Boolean cube. But that means that if I apply k to it, I should get a sum of squares of degree at most 2r. And so as long as this assumption is true, I have now found a representation of f plus lambda as a sum of squares. And so the immediate conclusion is that the gap between the degree r Lasserre bound, outer Lasserre bound, and the actual minimum is at most lambda. Okay, but this is really the sort of crucial starting idea, that you now have like a nice way of producing sum of square representations. Okay, so the problem is, how do we actually ensure that this condition holds, right? Like I say, okay, if this holds, then it's nice, but how do you actually make sure that this holds? Well, if you assume that k sends a constant function to itself, then you can rewrite this condition in the following way, by simply demanding that k inverse doesn't change polynomials of low degree too much, right? So what is going on here is that I know f is non-negative, and I know that if this condition holds, my kernel k never perturbs polynomials by more than lambda. Well, so that must mean that f plus lambda remains non-negative, right? Like my kernel is changing f plus lambda by at most lambda. So if f was non-negative before, it's going to be non-negative after. Okay, and it turns out that the way that we can now bound this quantity that I write here is by looking at the eigenvalues of the linear operator. And so intuitively, what this condition is saying is that k should be somewhat close to the identity, right? This is somehow what we want. And so we will be able to translate this by saying, okay, we want the eigenvalues of k to be somewhat close to 1. This is basically going to be the idea. And the key tool will be this Funk-Hacker formula, which is kind of a sort of classical thing in Fourier analysis, which is going to allow us to express the eigenvalues of this kernel in terms of q square in a very nice way. Namely, if we expand q square in terms of the Krautschuk polynomials, then the eigenvalues of our kernel will be exactly the coefficients in this expansion. Okay, and so this will give us a very nice understanding of these eigenvalues, which will then allow us to find a kernel with the property above. Okay, and so the next thing we're going to do is we're going to just recap some classical Fourier analysis on the cube to derive this Funk-Hacker formula. And then I'll also give a more precise statement. Okay, so this is step 2, so Fourier analysis on the cube. And here I'll go through this relatively quickly. It's not super important to understand this in detail, but I just want to sort of give the basic ingredients of what's going on. Okay, so you have these things called characters. So for each point in the cube, you define a character of the following form. And the point is that these characters form an orthonormal basis for the space of polynomials on the hypercube, right? So this quotient ring here, it's just polynomials divided by the equivalence that two polynomials I call equal if they agree on the binary cube. That's exactly what this space is. And so the characters form an orthonormal basis for the space with respect to the natural inner product, which is just summing over all points. Okay, so then you can decompose the space further in terms of these what are known as like harmonic components, maybe. So basically, you can write the space as an orthogonal sum of these hi, and hi is just the span of all characters corresponding to a point with Hamming weight I, right? Meaning I non-zero entries. And the idea is that these hi are invariant and irreducible under the symmetries of Bn. So it means that if I apply some symmetry of the binary cube to an element of hi, then I get something which is again in hi, right? It doesn't leave this space. Okay, so just using this decomposition, I can always decompose a polynomial in terms of these harmonic components. And the reason actually this is called harmonic is because you can also do this on the hypersphere in basically the same way, and then you really get harmonic polynomials. Okay, so how do the Krawchuk's enter in? So the Krawchuk polynomials I will just give here. They are the orthogonal polynomials with respect to a specific measure on R, namely the measure which assigns to each integer t between 0 and n the weight n choose t, right? And now the Krawchuk polynomials are just the polynomials which are orthogonal with respect to the corresponding inner product. And now there is a sort of key identity which sort of links all the elements on this slide together, which is the following, which is saying that the values of the Krawchuk polynomials are given by this summation formula, which I give here. And so in this summation formula, you can see that sort of all the components of this slide are there, right? Because you're summing basically over all characters which are in hi, right? That's what it means for Hamming weight of A to be I. And then you are taking a x and y, which are at distance k. And this is going to give you the Krawchuk polynomial of degree I evaluated in k. Right, so the Krawchuk polynomials sort of link these characters and harmonic polynomials in a way. Okay, so now I can give the precise statement of the Funk-Hecke theorem. So this was the thing we set out to prove in this section. So it's a classic result. So you have your polynomial q, and you have your decomposition of q squared in the basis of Krawchuk polynomials. And then the kernel corresponding to Q satisfies the given formula, right? So it's basically saying that the eigenvalues of this K are just equal to the lambdas which appear in the expansion of Q squared. And for the proof, really all you have to do, if you have the previous slide, is apply this key fact connecting the Krawchuks with the characters to show that actually if you apply K to a character, or to show that the characters are actually eigenvectors of the kernel, and that the corresponding eigenvalue is just lambda of the Hamming weight. Okay, and if you apply this, then you find the formula. Hopefully, I made this at least somewhat believable in the previous. Okay, so recall why were we doing this again? So we wanted to choose Q in such a way that K of 1 is 1, and this quantity below is small. Okay. But now if we look at the Funk-Hecke formula, we can actually reinterpret this in terms of the eigenvalues. So K1 being 1 just corresponds to lambda 0 being 1. And we can actually bound this infinity norm K inverse P minus P in terms of the eigenvalues. And here, the first inequality is really just using func-hecke. This is just giving you this first inequality. Of course, keeping in mind that the eigenvalues of K inverse are just the inverse of the eigenvalues of K. But now for the second inequality, actually, we have to do a little bit more work. So you can see here in the middle, we have this maximum over the infinity norm of the harmonic components of P. And now on the right, I have just replaced this by some constant, CD, depending only on D. And this is actually not trivial to see. So it's not trivial to see that if I have a polynomial P, which has an infinity norm of 1, that then the infinity norm of its harmonic components is also small. And in particular, that it does not depend on the dimension n, but only on the degree of the polynomial. But this is true. And yeah, I won't go into the proof here, but it's true, and it's not immediate. But I ask you to believe me here. And also what you can see is that I've sort of sneakily changed from the absolute value of 1 minus lambda I inverse to just 1 minus lambda I. And again, this is something you can just show. It's sort of a technical thing. But the intuition is just that if lambda I is close to 1, well, then lambda I inverse is also close to 1, and vice versa, right? And we do introduce this factor 2 to sort of make up for this, but that's essentially what's going on. Okay, and now we are at a point that we just want to find Q for which lambda 0 is 1 and lambda I is as close as possible to 1. Okay, and so we go to step 3, connecting this to the inner hierarchy. Okay, so just to repeat what we're trying to do, we're trying to find a Q which has this decomposition in terms of Kraczuk polynomials with specific demands on the coefficients. Okay. Now recall that the Kraczuk polynomials are just the orthogonal polynomials with respect to this measure, this discrete measure omega that I introduced earlier. And so these coefficients, because it's an orthogonal basis, you can just write in terms of these inner products, where I just have to normalize my Kraczuk polynomials, right? So this is just this equality here between lambda I and the inner product. This is just by definition of an orthogonal basis. And then this integral here on the right, this is just the definition of this inner product, right? And it's a bit weird to write it as an integral because it's really just a sum, but that's sort of the language which is more convenient here. Okay, and now we can rewrite our goal on the top of the slide in the following way. What we want to do is we want to find a Q such that the integral Q squared d omega is 1. This is just saying that lambda 0 has to be equal to 1. But also we want to minimize this thing here on the left. And if you look at this thing on the left, it's simply taking this sum 1 minus lambda I, and then I put all the 1's together, so I get a d, and I replace all the lambda i's by this integral of Kraczuk I times Q, right? So I've really done nothing here but sort of rewrite the problem on the top of the slide in a slightly more confusing way. But now, if you paid very good attention in the presentation, you'll recognize this as being an example of an inner Lasserre hierarchy, right? Because if you look at it, what are we doing? We are trying to find a density, a sum of squares density with respect to omega, and then we're trying to minimize G, the expectation of G with respect to this expectation. And of course, we want it to be an expectation, so we want Q squared d omega to be 1. But this is exactly what the inner Lasserre hierarchy was doing. Only now, instead of doing it on the binary cube, we're doing it on the interval. So we've sort of moved from a multivariate inner Lasserre hierarchy to a univariate inner Lasserre hierarchy, right? And so just to summarize, where we're at right now is, in order to now analyze the gap between the minimum and the order R outer Lasserre hierarchy for F, it suffices to understand the gap for the inner Lasserre hierarchy with respect to omega for G. Okay, so we have now we've expressed the error of the multivariate outer Lasserre hierarchy in terms of an univariate inner Lasserre hierarchy. And it will turn out, or it turns out, that this univariate inner Lasserre hierarchy is actually quite easy to analyze. And this will be the final step. Okay, so analyzing the inner hierarchy. And the key result here, which is a very special case of something shown by Monique and Etienne de Clercq. The point here is that for linear polynomials, the inner hierarchy is actually easy to understand. Namely, if your polynomial is linear and it achieves its, let's say, its minimum at 0, then the gap between the inner hierarchy and the actual minimum is just given by the least root of the corresponding orthogonal polynomial, which in our case is the Krautchuk polynomial. And this actually holds quite generally. So if you have any, if you're doing minimization over any interval with respect to basically any measure, then the inner hierarchy for linear polynomials will always correspond to the least roots of the appropriate orthogonal polynomials. And in our case, this will be Krautchuk. Okay, but there's a problem because the function g we're interested in is not linear, and so we cannot apply the theorem. But luckily, it turns out that g can be upper-estimated by its linear, let's say, Taylor approximation at t equals 0. Right, so g is upper bounded by its linear approximation, and if we look back to the definition of the inner hierarchy, this program, then we see that if you have a function which is strictly or just smaller than another function everywhere, then this infimum here is definitely also going to be smaller, right? Because I mean q squared is non-negative, so if I have a function which is upper estimating g, then the inner hierarchy for g is definitely going to be better than the inner hierarchy for this bigger function. Right, so let me write that down. The inner hierarchy for g is a better approximation, is what I'm writing here, than the inner hierarchy for its upper estimator g hat. But its upper estimator g hat is a linear function, and so I can apply the theorem. I know what the inner hierarchy is. It's just given by this extremal root of the Krautchuks. Okay, and now we are really almost done. All we have to do is understand this extremal root, and here we are lucky because these Krautchuk polynomials are well studied, very classical things, and so this result is just available to us. So we know that the least root of the degree R Krautchuk polynomial satisfies this inequality. And what we see here is just exactly the function which appeared in our main result at the beginning of the presentation. So now we are really home, right? And we are done. This is the end of the proof. So let me maybe give some concluding remarks. So what we've done is we've shown a quality guarantee on the outer hierarchy using a connection to a special case of the inner hierarchy. This is sort of the really high-level description of the proof. And actually, if you take this treatment on the final few slides of the special case of the inner hierarchy, you can actually extend this to the general case for the inner hierarchy, and this is what's giving our second result on the inner hierarchy. Okay, so as far as we know, this is the only analysis which works when R is smaller than half an n. So when the bound or when the hierarchy is not exact, but there is still a pretty large limitation, which I also alluded to at the start, which is that it only works if you take R to be a fixed fraction of n, of the dimension n. And so in particular, you basically get nothing if you take R fixed, just fixed. And this is in practice what people are usually a bit more interested in sort of convergence results for fixed R. But there we get no information. Okay, so then just to note, you can actually do this entire thing on the Q-array cube. So here we do it for the binary cube, but more or less the exact same arguments also work if you take the Q-array cube. And you get very analogous results. I mean, basically, there's like a Q analog of all these cross-jukes, of this symmetry reduction, etc. And you get very, very similar results. And then finally, maybe to give a possible direction for future research, is it possible to maybe add constraints to this, right? Because right now we are working with unconstrained Boolean optimization, but of course many problems you would like to be able to add, let's say, at least linear constraints, or maybe even polynomial constraints. But our analysis doesn't work if you do this. And so it's interesting to think whether it's possible to do something here. And maybe to note, there are some results for special cases. So for instance, if you look at knapsack, which you could write as like linear optimization over the binary cube with linear constraints, or I guess a single linear constraint, then we actually do have some convergence results about the Lasserre hierarchy, which is quite a bit better than what we show here. Right, so it's interesting to see maybe if we can do something with constraints, maybe in special cases, who knows? Okay, and so I think with that, I am done. I just list here some of the references. I guess if the slides are made public, you can look them up. And thanks for your attention.
Many thanks for this excellent talk. So I think we have plenty of time for questions. So please, if anybody has a question, just unmute you and ask a question. So there is nothing in the chat at the moment. So Victor Magron asks if this analysis could be extended to max-cut problems.
So I think as is, it does apply to max-cut, right? Because if I understand the question correctly, so max-cut you can already write as a unconstrained optimization problem. So in principle, this analysis would apply to max-cut. But I don't think that the result is perhaps particularly amazing if you really do this. Because of course for max-cut, I think more is known for the specific problem.
So you said if you fix the level of the hierarchy, you don't get good results. But in this case, you would probably use the first hierarchy, the first level of the hierarchy or something like Mann Williamson.
Yeah, exactly. So in like a
in this case?
No. So the analysis works for max-cut, but only if you take a level of the hierarchy, which is a constant fraction of n, which is something that for max-cut, I guess you wouldn't do, right? Because there's already results about maybe the first level. Yeah. So I mean, the theorem I guess applies, but maybe doesn't give a very good result, I suppose.
Other questions? So there is a question from, I don't know how to pronounce her name, Mai. Do you think that is the most expensive part in your method to apply binary polynomial optimization in practice?
Yeah, so to be clear, of course, this is not my method. So this is just the Lasserre hierarchy. But maybe to sort of maybe partially answer the question. So the problem is that, again, what we're looking at here is the Lasserre hierarchy at a level which is a constant fraction of the dimension n. And so when I say the Lasserre hierarchy can be computed efficiently, this is only if you fix the level, right? But we don't. And so just computing this Lasserre hierarchy in general is very expensive. Like if you want to compute the, I don't know, the 20th level of the hierarchy when n is 100, this is like completely, I think, completely infeasible already. Yeah.
Okay, there is another question. So by the way, of course, you can pose your questions yourself if you want. Frank, do you want to ask the question, or should I moderate? So how does the convergence rate change when going from a binary cube to the unit sphere? Frank Valentin asks.
Right. So the main difference is, of course, so on the binary cube, the hierarchy converges in finitely many steps, right? It's this result that I gave. But on the hypersphere, it doesn't, right? So on the hypersphere, you can have instances where the hierarchy never converges. I mean, it converges asymptotically, but not finitely. And so on the hypersphere, the result that Fang and Fazi give is in terms of like a fixed n, and then r is going to infinity. And basically what they show is that as r grows, the gap between the hierarchy and the actual minimum is roughly 1 over r squared. And so their analysis is really sort of asymptotically in r. Yeah, so I hope that...
I remember also a paper from Stefanie Wehner about, I think it was the unit sphere or something, but I don't know if the degree or a number of variables was fixed.
So,
and the question is, do you know that paper? It's a bit older, and it might be with similar methods actually, because you said you use the methods of Fang and Favzi. But I wonder if similar methods have been applied before. This was a paper in, it was in physics terminology. It was not easy to understand, at least for me. Do you know?
Yeah, so yeah, I know the paper. It was also not so easy to understand for me. Yeah, so what they do is they work in the same setting as Fang and Fazi, and they show 1 over r, so slightly weaker than 1 over r squared.
On the unit sphere?
On the unit sphere, yes.
Okay.
And indeed, their proof is in this language of tensors and physics, and it's not completely clear to me. So there should be, I think there should be some connection between what they do and what Fang and Fazi do, also because they essentially also bound both this outer and this inner hierarchy. It's both in their paper, but it's not completely obvious to me how it would be the same method. And they also, of course, find a slightly different result. So yeah, we have looked at this, but it's not something I don't understand completely what the connection would be, but probably there is some connection to be made.
So Victor Magron asks, is there a connection between your orthogonal polynomials and the Christoffel-Darboux kernel associated to the measure omega? So maybe, Victor, you want to explain what is the Christoffel-Darboux kernel? There was a lecture on this, but...
Yeah, so maybe what I can say about this, so I'm not an expert at all on Christoffel-Darboux kernels, but what I can say is that like there does seem to be, like the results that you get for this inner hierarchy and the results that you get for these Christoffel-Darboux kernels, they do often sort of look the same. So you get like similar type of convergence results. But I don't know if there's any like direct connection between these two. Like it would be interesting to know this, but I don't know.
So Victor says it's the sum of squares. The Christoffel-Darboux kernel is the sum of squares of orthogonal polynomials associated to the measure.
Yeah. So again, I would not be surprised if there is a connection, but I don't know. It's actually something. Yeah, I would be very interested if someone knows this.
So when you generalize the method to these hypercubes so if you have a non-binary case, if you have instead of just 2 bits, instead of just 0 and 1, you have 0 up to q or something like this.
Mm-hmm.
What do you replace the Hamming distance with? I mean, is it just
You keep the
count the
Hamming
different
distance.
entries, or do you look how far the entries are from each other? Or
Yeah, so you keep the Hamming distance. So it's just the amount of different entries. You don't care how different.
mm-hmm.
Yeah, and actually the like the symmetry will be very, very similar, and all the like this entire Fourier analysis is almost the same. You just have to replace sort of the things that need to be replaced, but nothing really special happens.
And you said that your result gets better if a number of variables gets bigger. That's quite astonishing. Usually it's
okay, so it gets better, meaning. So what I meant by that is that there is this error term in the result, which is depending on n. So okay, maybe to explain this, so we keep in mind that like we always look at a order r, which is a constant fraction of n. So if I increase n, then I'm also increasing r. So this is why it seems to be contradictory, but that's the point, right? So my analysis gets better, but also the degree of the Lasserre hierarchy gets bigger.
Yeah, but still it's, I don't know. Okay.
But this is basically, I guess this is basically because like the result about these extremal roots of Quadratic polynomials, it gets more precise if n is bigger. I guess.
Okay, any other questions?
Yes, I have a question. Can you so you mentioned the QRE cube. You extend it? Can you extend it to other finite sets like simplex, scale simplex, or more general?
So maybe, but I guess what you really need is to have a nice symmetric structure that allows for this symmetry reduction. And I do know that in the paper by Fasi, Perillo, and Sanderson, where they show exactness, they actually also do this on, I think, maybe the cyclic group, and maybe they have even a few more examples. So these would be sets to look at. But like I said, you need to have a set which has like a very nice symmetric structure. Otherwise, it won't work. So maybe the simplex is somehow possible, but you would definitely need to do something.
Thank you. And maybe another question, if possible. The bound you give here, is it sharp?
No. So and you no. So I mean, it's definitely not going to be sharp. I guess for a few reasons. So first of all, this result we use on the Quadratic polynomials is not sharp, right? So immediately, if you would have a better result on these roots of Quadratic polynomials, you would get a better bound here. But even beyond that, I guess we are simplifying the problem a lot, right? So we're looking, for instance, only at these polynomial kernels which have a very special form, because then we can analyze them. But it's very well possible that if you take a kernel with a more general form, that you might be able to get a better result. And in particular, I guess if you look at our result, it's never giving you it's never actually giving you exactness. Whereas we know that sometimes this Lasserre hierarchy converges very quickly, right? I mean, in particular, if you take f to just be a square, then it will converge very quickly. But our bound doesn't tell you this. So no, it's not sharp.
Thank you.
I see that Victor posted some more information on the Victor Darboux kernel in the chat. Were any other questions? I have one more question. So in some sense, from what I understood, you somehow round a polynomial which is non-negative on the hypercube, you round it to a sum of squares after adding some constant, right? Is that true?
Yes, I'm not sure if you're rounding it. I guess you're giving a representation.
Yeah. Okay, but can you also work on the dual side, or I would actually call it a primal side? So could you start with pseudo moments, like this is a linear form that maps the sums of squares to non-negative numbers, and 1 to 1, and then round it to actual moments of a measure?
Maybe. So we haven't looked at this yet, but I can say that again in this paper where they show the exactness, they do actually give this dual side of the story as well. So this might be something to look at actually, if it makes sense to do this on the dual side. But we have not looked at this yet.
So may I say a word?
Yes, please, Monique.
So you are asking about what about if you start from the dual side, from the moment. So yeah, maybe what I can say is that actually this is maybe what they are doing in this paper by Stephanie Weiner, which you mentioned. So they solve the moment relaxation, and they get the moment matrix, positive semi-definite, which they use to create a sum of square density, which is then used to bound the upper bound. I mean the outer or the inner. Anyway, the measure-based hierarchy. So they start from the moment and they deduce something for the measure-based upper bound. But apparently, this is what we don't understand. But apparently, this yields a weaker convergence analysis is in just 1/r, for instance, for the sphere. While the true value seems to be 1/r square, as shown by Fuzzy.
Okay.
So that's
sorry. So more questions? So we have still 7 minutes. I don't know, what is our policy? Do we make a break if there are no more questions, or?
Yes.
You should wait, right?
yes,
Yes,
it's
Marcus.
a 5 minutes break. Yes.
So let's make a break until +2. Okay, many thanks again.
Yes. Okay.